Hello everyone, welcome to the video tutorial on Firebird V robotics research platform. This platform is based on the LPC2148 microcontroller from the ARM7 family. In this tutorial, we will learn about stepper motors, ways to control them, and how to interface stepper motor with the Firebird V robot. Let's see the agenda for discussion in this tutorial. First, we will have an introduction where we will discuss what is a stepper motor and its types. Then we will move on to learn how to control a stepper motor in different stepping sequences like wave, full, and half stepping modes, followed by a comparison of the three stepping modes. Then we will have a short demonstration of how to identify the wires of a usually unlabeled stepper motor. This will be followed by a discussion of the circuitry required to drive a stepper motor, and then finally we will jump on to actually programming the robot to control the stepper motor. So the first question that arises is, what is a stepper motor? A stepper motor is a special kind of motor whose rotation is divided into discrete steps which allow precise control over its angle. It can be commanded to hold a step or move to the next step. Types. Steppers are mainly classified on the basis of the internal wiring. These classes are as follows. Bipolar stepper motors usually have 4 wires to control them, and the drivers are complex. Unipolars, on the other hand, have 5 or 6 wires and are relatively easier to drive. Since unipolars are more commonly used, we will be using them in this tutorial. Moving on to how to control a stepper motor. A stepper motor can be controlled by sending specific sequences of signals to its wires. The different stepping sequences are wave stepping, full stepping, and half stepping. We will now see and understand how to use each one of them. Wave stepping. It involves exciting each coil turn by turn in a circular fashion. The table shows which coils are to be excited for generating the wave stepping sequence. Here, a 1 denotes on, whereas 0 denotes off. To rotate the stepper motor in one direction, we send the sequence 1, 2, 3, 4, 1, and so on, while for the opposite direction, we send the sequence in reverse, that is 4, 3, 2, 1, 4, and so on. Shown here is an illustration that depicts the direction of the rotor inside a stepper motor in the wave stepping sequence. The rotor points to the excited coil at that instant. When coil A is excited, the rotor aligns itself to point to it. Next, when coil B is excited, the rotor turns to align itself again. This process repeats for the other coils. Full stepping. It involves exciting 2 adjacent coils turn by turn in a circular fashion. The table shows which coils are to be excited for generating the full stepping sequence. Notice that at each step, exactly 2 coils are excited. Now let's see what happens inside the motor when 2 coils are excited at once. As you can see, when 2 coils, say A and B, are excited, the rotor settles between them. This results in a higher torque than that found in wave stepping. Half stepping. This stepping mode is a combination of wave and full stepping. Now, if you look closely, half stepping uses full stepping between the step positions of wave stepping. Let's see what happens inside the motor during the sequence. As you can see, there are 8 positions corresponding to the 8 steps shown in the previous table. It is called half stepping because it effectively halves the step angle and offers more resolution. We will now see the differences and similarities between the three stepping modes. Talking about torque, since only one coil at a time is energized in wave stepping, its torque is the lowest. In full stepping, two coils are excited at once, creating a larger attractive force, resulting in a larger torque. Since half stepping excites one or two coils per step, the torque output is intermediate. Vibration in a stepper motor increases with torque and decreases with the step angle decreases. Since wave stepping has a low torque but a step angle larger than half stepping, it has an intermediate level of vibration. Full stepping, on the other hand, has higher torque resulting in more vibration, and half stepping, due to small step angle, exhibits the least vibration. Next is speed. Speed is equal to the step angle times the step frequency. Since the step angle is the same for wave and full stepping, they have the same speed. For half stepping, the stepping angle is halved and thus the speed is also halved. Resolution is fineness of control over a rotational angle and is equal to the step angle. The step angle is equal for wave and full stepping while it is halved for half stepping. We will now learn how to identify the wires of a stepper motor.
Most of the stepper motors do not come with the wires label or some data sheet specifying it. So to figure out which wire is which, let me show you a simple way to do it using a multimeter. Take the stepper motor and strip its ends if it is not already. This one is a 6-wire unipolar stepper motor and has two common wires. To identify them, connect one wire to one leg of the multimeter and serially try to check the resistances with each one of them. The second wire shows a resistance of 7.5 ohms. The third wire shows an open connection. The fourth wire again shows 7.3 ohms. Thus we have identified a coil whose center tap is the first wire, that is the green one, and it ends being the second and the fourth. Repeating the process for the open wires, let's connect one leg to the third wire, that is the orange one, and the other to the fifth one. This shows a resistance of 13.5 ohms, which seems to tell me that I have the opposite ends of the coil, and the last one, that is this one, is the common wire, that is the center tap wire. Seeing the resistance with the last wire indeed shows me 7.3 ohms. By this we have identified that the green and the black wires are common wires. We will short them together and treat them as one. Note that the order of the four wires cannot be determined by this method. This can be only found by actually running the stepper motor with random assignments of connections and snapping the last two if it just wobbles instead of rotating.
This is a circuit diagram for the stepper motor driver. The ULN2003 is a transistor array package of 7 transistors that are capable of switching 500 milliamperes of current per transistor. The pins 1 to 7 are the inputs to the transistors, while the pins 16 to 10 are the corresponding open collector outputs. All transistors have a common emitter that is connected to the ground at pin 8. The COM pin at pin 7 is connected externally to the supply voltage. The circuit is basically used to drive the stepper's high current windings by a microcontroller's general purpose I/O pins. We will now discuss how to interface the ARM7 based Firebird V robot with the stepper motor using this circuit. These are the Firebird V robot's JTAG connector pins, which we are going to use to connect to the driver circuit shown previously. Pin 11 on the JTAG connector, that is P1.26, is connected to the ULN 2003 driver IC's pin number 1. Pin number 13, that is P1.27, is connected to the driver IC's pin number 2. Pin number 5, that is P1.28, is connected to the ULN 2003 driver IC's pin number 3. Pin number 9, that is P1.29, is connected to the ULN 2003 driver IC's pin number 4. Pin 4, that is ground, is connected to the ULN 2003 driver IC's ground on pin number 8. The pins are numbered on the connector as shown in figure. We will be using the pins 11, 13, 5, 9 and 4. The numbering is done assuming you are looking into the 20-pin FRC connector on the Firebird. Now for an example, we will be rotating the stepper motor in one direction at a fixed speed for a complete revolution and then change its direction and repeat the process in the opposite direction. For this, we can either use delays between steps or we can use one of the timers for the delays. For this video, we will be using simple delays for the job. This is a list of headers to be included, which are LPC2148H and a custom header called stepper.h that contains the functions for controlling the GPIO pins of the stepper in different step modes. Moving on to the main function, first we initialize the IO ports for the stepper motor. Then, in an infinite loop, we have a call to the function full_step, which takes direction as argument and is defined in stepper.h and will be discussed in the next slide. This is followed by a delay of 10 milliseconds so that the resulting step frequency is 100 Hz. Direction here is a global variable that is initially set to +1 and is changed to -1 after every 200 steps by the following code, which increments count in each iteration and changes direction from +1 to -1 and vice versa if count exceeds 200. It then resets count to 0. Stepper we use completes a revolution in 200 steps. Modify this value if your stepper motor's steps per revolution value is different. Now let's have a look at the port initialization function. Stepper_port_init. This function starts by setting the pin cell 2 registers bit 3 on and bits 2, 1 and 0 off. Bits 1 and 0 are reserved bits and bit 2 is set to 0 to disable JTAG functionality of the pins to allow us to use them as GPIO pins. The second line sets the 4 pins as output pins as specified in the hash-defined constants coil A pin, coil B pin, coil C pin and coil D pin in the register represented by the constant stepper port dir, which equals IO1 dir, that is the port direction register for IO port 1. Using hash-defined constants for ports and pins allow greater flexibility and reusability of code should you later decide to use another port or pin. Although it is used only once here, it will be used more often in the step functions that we discuss later. Now let us try to program the robot in Keil Microvision 4 IDE. Follow the usual steps of creating a new project and configuring the project for use with the LPC2148 microcontroller. Here I already have the project set up. As you can see, the first two lines are the include directives for the LPC2148 library and for the stepper.h custom header file, which we will discuss in a short time. The first function is a simple delay function that generates a delay of roughly j milliseconds, where j is the argument passed to this function. Note that this method generates inaccurate delays as it depends on the execution time of the code, and it varies with compilers and the level of code optimization. The next two lines are the declarations of the two global variables direction and count as explained earlier in this tutorial. This is followed by the main function, which has also been explained earlier. Moving on to the stepper.h header file, which contains the code to control the stepper motor in different step modes. The first two lines are used to avoid users of this header from accidentally including the file twice. Don't worry if you don't understand how it works. Moving on to the subsequent lines, we come across the hash-defined constants used in this file and specify the port and pins at which the stepper's wires are connected to. The set, CLR, and DIR constants can be set to the corresponding registers of the port being used. The subsequent lines specify at which pin numbers of the port the wires are connected. The following function is a stepper port initialization function that is already discussed earlier. Next is the wave step function that takes in the direction argument and takes a step in that direction. The first line declares a static variable step index that stores the number corresponding to which step of the sequence the stepper is currently in. The first line declares a static variable step index that stores the number corresponding to which step of the sequence the stepper is currently in. The next line either increments or decrements the step index based on whether direction is 1 or -1. The expression adds 4 and a modulo 4 is performed to continue from 0 if step index goes to 4. The effect is that step index is always 0, 1, 2 or 3. Then depending on the value of step index, we send the corresponding step sequence. Here, stepper port set is assigned a value of 1 left shifted by coil A pin bits, which has the effect of setting coil A pin to 1. Similarly, the next three lines set the other pins to 0. The other case statements in the switch block send the corresponding bit pattern as discussed in the wave stepping section previously. Similarly, the next function full_step achieves a similar purpose, but for the full stepping sequence. The only difference here is in the bit pattern being sent. The next function is half_step, which also works similarly, except that it has 8 steps and so its expression adds and divides by 8 instead of 4. The switch block here has 8 cases, that is, from 0 to 7 for each of the bit patterns of the half-stepping sequence. Now let's build the code and burn it on the robot. We will now see the stepper in action in the following clip. So by now, we have successfully understood the control of stepper motors and how to interface a stepper motor with the LPC2148 based Firebird V robotics platform. You may modify the code to experiment with different stepping modes, or by setting it to specific angles, or by using timers, or basically anything that your imagination leads you to. With this, we have reached the end of this video tutorial. Thank you for listening. For any doubts or suggestions, feel free to mail them at helpdesk@e-yatra.org. This is Joel Pinto signing off.